When we were calculating cell potential earlier, we said the cell potential is measured at 1 atmosphere, 25 degrees Celsius, and concentrations of 1 molar. There are equations that relate temperature and changing pressure to the cell potential. They are much more difficult and require calculus. We are only going to look at the equation where we change the concentration, the nernst equation. The nernst equation is the cell potential is the standard cell potential minus RT over NF times the ln of Q. Remember where Q is the initial concentrations of products over reactants raised to their powers, okay, of the reaction. So of the variables up there, R is 8.31 joules per mole Kelvin. T is temperature, 25 degrees Celsius or 298 Kelvin. N is the number of moles transferred in the reaction. And F is Faraday's constant. So of these numbers, some of these do not depend on the reaction you're dealing with. So R is always 8.31. Faraday's constant is always 96,485. The number of moles being transferred will depend on the reaction. Sorry, Faraday's constant goes on the bottom. And the temperature is always 298 Kelvin. Now, so these three numbers right here are always going to be the same, all right? So what they do is you can combine those three numbers together and change it from natural log, in other words, base 2 into base 10. And what that does is it simplifies the equation to the following. Okay, so by changing it from base 2 with the natural log to base 10 log, it combines and turns into 0.0591. Okay, so let's do an example problem here. How about we do let's see. Well, why don't we stick with that reaction we were doing before and just change the concentrations. So we had manganese, and we had all right. So the overall reaction was this. All right, now let's just say that our concentration of the iron was 0.2 molar and the concentration of the manganese was 0.150 molar. So they're not at 1 molar concentrations, okay? So to figure out the new cell potential with the different concentrations, we would plug in 1.1144 volts minus 0.0591. Now, how many electrons are being transferred in this reaction? 6. So we would divide by 6, and then we would multiply it by the log of Q. Now, Q is the products over the reactants, and we do not include solids in our expression. So we are just looking at the concentration of manganese, raise it to a power of 3, over the concentration of iron, and we raise it to a power of 2. So Q is going to be 0.15 raised to the third power over 0.2 raised to the second power. Something weird happened here. Well, I don't know what's going on, so I'm going to have to figure it out down there. So 0.150 cubed divided by 0.2 squared. So my Q my Q is going to be 0.084. So then when I plug it in for the log, so the cell potential is going to be 1.140 minus 0.0591 over 6 times the log of 0.0843. So then my new cell potential will be it actually doesn't change it that much. It becomes 1.13 volts. Okay, I'm just going to double check that calculation one more time. I got a little different number that time. Let me try that one more time. Actually, it's the other way. It's 0.15. So yeah, I messed that up. So by changing the concentrations, we actually increased the voltage. So you'd think it's not just the size, it's not like increasing the concentration makes the voltage greater, it's the ratio of the top number to the bottom number that matters. Okay? So I seem to have figured out what I was doing wrong there, so I'm just going to quickly, you can either end the video now, or I'm going to just recalculate that there by showing that on the bottom we got 0.2 to the second. That comes out to be 0.0843. Then you plug it in. Don't forget your negative sign. And so this comes up to 1.15 volts. So by decreasing the concentration, we actually increase the voltage.